All right, we're pretty much done. We just got a little summary and practice section here. We'll start by saying that I have F. I get an F for my alphabet skills. We'll start with a bit of a review. A little summary, a little unit summary. The normal distribution models the continuous distribution of populations. When I say populations here, I'm just referring to the fact that, if we talk about like animals or like plants, like height and weight and all this stuff, a lot of those are very normally distributed. Okay. It's not actually the only way of interpreting that sentence, but it's one. It's identified as a bell-shaped curve. Normal models are only appropriate for distributions, remember, that are continuous, symmetric, and unimodal. We won't use it really much for other things. Sometimes we'll approximate discrete distributions with continuous distributions, but that's generally the case. And the standard normal model, or standard normal model, if you will, has a mean 0, standard deviation of 1, has to do with z-scores, counting how many standard deviations above or below the mean we are. So we have this formula. Let's find some probabilities. So first example is find the probability that z, and remember, if we want a value, that's lowercase, but that refers to a capital Z, which is always going to be standard normal. So find the probability that you would be less than 1.5 standard deviations above the mean, right? Z-score, this means 1.5 standard deviations above the mean. What's the chance that we're less than that? Well, it's pretty straightforward and similar to what we've done before. We just go on GeoGebra. Standard normal means mean 0, standard deviation 1. It is also what GeoGebra defaults to. What's the probability that we're less than 1.5? 93.32%. That's all there is to it. What's the probability that we're bigger than about 1/3 of a standard deviation below the mean, but also smaller than 1/2 of a standard deviation above the mean? Well, we just go and do the same thing. Click the between button. And over here, write -0.3. Over here, write 0.5. That gives us our probability. We can see that probability is the same as what percent of the area is shaded. And either way, we'll get about 30.94%. That's how we can work with standard normal stuff. Let's do one more example to finish off the unit. An incoming freshman took her college placements exams in French and mathematics. French, she got an 82. Let's color coordinate. French, she got an 82. And in math, she got an 86. The overall results of French was a mean of 72 and a standard deviation of 8. Whereas math, the mean 68, standard deviation was 12. So what did she do better relatively on? Because obviously we can look and say, okay, she scored higher in math than French. But what's more interesting is, relatively speaking, if it was like on a curve or something, how does she compare to her classmates in these two things? So let X, let X equal the score of, some freshman, a random freshman, in French. And we'll do something very similar. Let's let Y be the score of a random freshman in math. We know that X is roughly, well, we don't know that. It didn't tell us that. Well, let's assume it. Yeah, raise your hand, ask a question, say, Jason, can we assume that these are normally distributed here? Because it doesn't say. We'll assume it. Normally distributed with a mean of 72 standard deviation of 8. Whereas y is normally distributed with a mean of 68 in math and standard deviation of 12. And we want to know how she did. So we could draw both models and try to like figure it out, or we could just standardize. Let's find each one of their z-scores. So the z-score is just going to be x minus mu over sigma. What is our x here? She scored an 82. And it was an 86 in math. All right, so we got 82 minus the mean, which was 72, over the standard deviation, which was 8. It's going to simplify down to 1.25. Again, remember that if you're using a calculator, make sure to use parentheses. 82 minus 72 over 8, 1.25. So she's 1 1/4 standard deviations above the mean in her French class. Whereas over here, for math, she scored an 86. The mean was a 68. It was a lower mean, but a bigger spread. Okay, so we don't know how many standard deviations above this is. But if we calculate it all out, we get 18, which is 1 1/3, I think. I'm going to type this on a calculator. 86 minus 68 over 12. Okay, nice try, Jason. This is why I check with a calculator. 1.5. So what did she do better on? Math. Okay. And it wasn't just because the math was a higher score. It wasn't just because the average in math was lower. Combination of all those things with the standard deviation. You did better in math. 1.5 times standard deviation above the average. That's how you can use standard normal distributions. There we go. You have apples, you have oranges. Can't compare apples to oranges. We turn them both into tangerines, which are kind of like oranges, so maybe not the best metaphor. Kiwis. I don't know. Pick your fruit. There we go. That's standard normal distributions. That's normal distributions. Remember, standard normal distributions are just special cases of normal distributions. They have a very special mean and standard deviation, specifically 0 and 1. Very nice numbers. Not a coincidence. And this is what we're going to use for continuous distributions. This is mostly the only continuous distribution we're going to look at in this class, the normal distribution. We had discrete in the last unit. That looked like this. These were discrete. You can see specific. Here's the probability for 10. Here's the probability for 11. Whereas continuous, well, there's everything in between. All right. And we can use GeoGebra's calculator to help us out with those calculations. Anyway, hope you enjoy the homework, or at least don't hate it that much. Hope you learned something, and feel free to ask me some questions if you have them. Bye-bye.